In this video, we're going to take a more quantitative approach to defining what we mean when we say small signal. So how do we determine if an AC signal is small enough in order to use the techniques we're going to talk about? And so what we're going to do is we're going to start with some equations we had from the previous unit where we defined our collector current and our base current in terms of sort of our base emitter voltage and our thermal voltage, our reverse saturation current, and all of those types of things. So in general then we can say that our base current, again from the previous unit, we said that was equal to the reverse saturation current divided by beta times the exponential of our base emitter voltage divided by our thermal voltage Vt. And again, we can basically see right here we have the expression for our collector current, and we just divide that by beta to get our base current because again, we're going to be working in the forward active mode. All right, another thing to point out too is of course I have a lowercase parameter with uppercase subscripts here and here indicating that these are the combination of our DC and AC components. So to show that a little more explicitly, let's go ahead and separate that out for our voltage term. So we still have the IS over beta. Those are both just constants. At least we're assuming they're constants. They will have some temperature dependence, but that's kind of beyond the scope of what we're considering. So our VBE, let's go ahead and break that up into our VBEQ, so the DC value at the Q point, plus our small signal VBE, so that's our AC component. So both of those are divided by our thermal voltage, Vt. All right, so now we can use properties of our exponential function and we can break that up into two terms. So we can say this overall base current is equal to IS over beta times the exponential of VBEQ divided by Vt times the exponential of our AC component, VBE, divided by Vt. And what we can recognize then is that this first part here is just going to be our DC base current. So we can now write this as IBQ in place of that term that's circled in the yellow highlighter times exponential of VBE over Vt. But now remember, we kind of already knew this from the previous video. We know that we have some exponential relationship between our base current and our base emitter voltage. But ultimately what we want to do is we want this to be linear. So we want a linear relationship between our base current and specifically our AC base current and our VBE. And so now, of course, we can't change the properties of that. We can't magically make it be linear instead of an exponential relationship. But what we can do is we can approximate. And so we can linearize that and approximate a linear relationship under certain conditions. And so the way we're going to linearize this is we can use a Taylor series. So using a Taylor series expansion, and then we have to have one sort of key thing be true. So this argument of our exponential here has to be really small, and if it's really small, we can neglect the higher order terms in our Taylor series expansion. So what we can say is in this Taylor series expansion, if our VBE is much less than our thermal voltage Vt, then we can ignore higher order terms. Okay, so here's sort of a key thing here. We're saying this is sort of the limit for our VBE. And so if we do that and we ignore our higher order terms, what we end up getting is this expression up here can be linearized and rewritten as IB is approximately equal to, because again, of course, we're approximating. So we still have that IBQ out front, and then we linearize that exponential term, and it becomes 1 plus VBE divided by Vt. So that's sort of our linearization there. And so, of course, what we can do is we can split this into the two components. Let's go ahead and multiply that IBQ through. So we have IBQ plus our IBQ times VBE, and so that should be lowercase VBE, divided by VT. And so now remember, in a couple videos back, we had said that in general, our IB is equal to some DC component plus some AC component. And so comparing these two equations for our IB, we can say that this is then going to be our DC component, and this is going to be our AC component of the base current. So that would be capital I, capital B, and lowercase I, lowercase b, respectively. So now we have that desired linear relationship between our lowercase ib, which is equal to some constant value, which is going to be IBQ over VT, times our VBE. So this is our desired linear relationship. Okay, and so a couple of things to point out about this. First of all is we see that this is dependent on our Q point values, so that's something I'm going to continue stressing. So our Q point is very important for multiple reasons in our AC analysis. So it's dependent on this Q point value, and if we think a sort of a step further back to the plot we saw in the previous video, we can see we can relate the slope of that plot to this term here in parentheses. So we see the slope of that linear approximation is going to depend on where we're at based on our DC analysis. So the second thing I want to do is sort of revise this a little bit. So I was very vague and I said we can ignore these higher order terms if our VBE is much less than VT. Well, let's take a closer look at that and see if we can get a better idea of what VBE values we're talking about. So recall that at room temperature, our thermal voltage is about 26 millivolts. So because of that, our general rule is that our VBE should be less than 10 millivolts. So our general rule is that that small signal VBE should be less than 10 millivolts. And if that's the case, then we can say we have a small signal AC signal. And then all the analysis techniques that we're going to look at later are going to be appropriate. And again, you might be saying, well, 10 isn't really much less than 26. And again, just keep in mind that's sort of the upper limit that we're allowing. And you're definitely going to see some distortion even as you get close to that limit. And so what happens when these signal amplitudes get too large is a good question to ask. It's something that we're not going to really go into, but I want to at least briefly mention it. So when our signal amplitudes are too large, what we end up getting is nonlinear behavior. So our amplifier shows nonlinear behavior, as you would expect. And of course, a lot of these techniques that we're going to talk about based on superposition aren't going to be valid, because if we don't have those linear signals, then we can't use superposition to combine them. And so typically the way this is manifested is through harmonic distortion. So this can be seen as harmonic distortion. And again, this isn't something that we're really going to talk about much at all beyond just mention it. If you do want to see a little bit more, there's a few more details on page 375 in the textbook. But of course, this is a topic that you can look up and find a fair amount on just sort of with some basic research. So now that we have a better idea about what we mean in terms of small signal, we're ready to start creating some models and building some amplifiers.